तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the previous lecture, we completed the discussion on bipolar junction transistor. In this lecture, we shall begin a new topic, that is the metal oxide semiconductor junction. Now, for reasons that we will discuss, this structure, that is a metal oxide semiconductor junction, is very often called the capacitor. Now, let us see what we will try to address in the next few lectures. The most important thing that we would like to explain for the MOS junction or the MOS capacitor is the CV characteristics shown in the following slide. So, let us look at the characteristics in detail. On the x axis you have the voltage, and on the y axis you have the capacitance of the structure divided by C naught. We will see what C naught means. Basically, this is a normalized capacitance. So, here you also have the biasing arrangement under which the capacitance characteristics have been measured. So, you have a DC bias applied and a small signal is superimposed on the DC bias. So, this is a sinusoidal small signal voltage. Now, the capacitor is a two-terminal device. The structure is that there is a semiconductor. In this particular example it is p type. Then on the semiconductor you have a silicon dioxide layer which is shown by this hatched portion, and then on the top of this silicon dioxide layer you have a metal electrode. Now, between the metal electrode and the p-type semiconductor there is a capacitance that is being measured. Now, how do you know that there is a capacitance here between these two in terms of the terminal characteristics? Well, when you apply a small signal voltage, there is a current, small signal current that results in the circuit. The relation between the small signal current or the sinusoidal current and the sinusoidal voltage tells you whether the structure is resistive or capacitive. If it is a purely capacitive structure, then the phase difference between this current and the voltage indicated by phi here would be 90 degrees. The omega here indicates the frequency of the small signal. Now, when you vary your DC voltage as shown in the x axis here, you find that the capacitance of the device is constant over a certain range, and then beyond a voltage indicated by the symbol VFB or the flat band voltage, the capacitance starts falling. Now, in this region what you find is that the capacitance is independent of the frequency of the signal, but beyond this range, as you move to the right, you find the capacitance for different frequencies is slightly different. until you come to this point here, which is called the threshold voltage denoted by the symbol Vt. The capacitance falls, and at high frequencies the capacitance beyond this Vt point or threshold voltage point saturates. At very low frequencies of about 10 Hz or lower, however, the capacitance rises again, okay, to the value that you had for very high negative voltages. Okay. Now this is the characteristics assuming a p-type substrate. So we would like to explain this variation in the capacitance as a function of voltage and also as a function of frequency, and then we would like to derive formulae for the VFB, that is the flat band voltage, and Vt, the thermal voltage. Now let us explain what is meant by this C0 capacitance, which is used for normalizing the capacitance of the device. Now this C0 can be explained as follows. This is your structure. So this is the metal, this is the silicon dioxide, and this is the semiconductor. Which is silicon. So O stands for oxide, silicon dioxide. Now C0 indicates the capacitance of a structure which has metal electrodes on either side. Okay, so this is metal, this is oxide, and this is again the same metal. So this is a normal parallel plate capacitor containing the oxide layer as the dielectric. Now the thickness of the oxide layer is the same as the thickness of the oxide layer in the actual MOS capacitor. So capacitance of this particular structure is C0 between these two terminals, whereas the capacitance of this structure, which is our MOS structure, is C. So C normalized with respect to C0. So what this curve in the slide shows is that the maximum value of the capacitance of the MOS structure is equal to C0. Now we shall discuss the capacitance voltage characteristics in the following manner. Okay. So first we will discuss the device structure and how it is fabricated. Then we shall discuss the charge voltage characteristics. The Q here stands for charge. In the charge voltage characteristics, first we will discuss the idea of an ideal MOS capacitor. Please note that we are using the words junction and capacitor interchangeably. Okay. This is because for the MOS junction there are no characteristics other than the capacitance characteristics. For a PN junction you have the current voltage characteristics. Okay. That is a DC current voltage characteristics. For the capacitance, however, you do not have any DC current voltage characteristics because there is an oxide layer that insulates the metal from the semiconductor. When you apply a voltage to the structure, there is no DC current. However, when you apply an AC voltage, there is an AC current. Then after discussing the ideal MOS capacitor, we will discuss the accumulation, depletion and inversion regimes of operation. Then we will define the threshold voltage and flat band voltage and derive formulae for these two. and we will see the energy band diagram of the device. Now, most of the analysis that we do, we will be doing without the help of energy band diagram, using the concentrations of electrons and holes within the semiconductor as a function of the voltage or electric field. This is what we had done even in the case of p-n junction, and then we will point out exactly at what point we need the energy band diagram. After discussing the QV characteristics, we will discuss the capacitance voltage characteristics derived from the QV or charge voltage characteristics, both under low frequency and high frequency conditions. And finally, we will discuss a 3-terminal MOS structure and an effect related to this, namely the body effect. So now let us start with the device structure and fabrication. Now we said this is the device structure where you have a silicon semiconductor. This could be either p type or n type. We will consider for all our explanations a p type semiconductor. On this p type semiconductor, the oxide layer is grown by heating the semiconductor at very high temperatures. Now generally the oxide layer is grown in the presence of pure or ultra pure oxygen at temperatures as high as 1100 to 1200 degrees centigrade. Okay? The time of this oxidation is a couple of hours, and it results in oxide thicknesses which range from about 100 angstroms to 1000 angstroms. In modern days, the technology has advanced, so we can have very thin oxide layers of very good quality. Now it is very important that this oxide layer be of high quality. That means its dielectric constant should be high and it should be very insulating. Now after the oxide layer is grown on the p-type semiconductor, we deposit a metal contact. The metal layer is generally made of either aluminum, or in modern days the metal layer is replaced by a heavily doped polysilicon layer, which also acts like a metal because its conductivity is very high. So although we use the nomenclature M here stands for either a metal layer, in which case it is mostly aluminum, or a heavily doped polysilicon layer. So metal, usually aluminum, or heavily doped polysilicon. Now when we say heavily doped polysilicon, it obviously means that the doping can be either n type or p type. Okay? So you have MOS capacitors with n plus polysilicon, or you have MOS capacitors with p plus polysilicon. So just as substrates can be p or n type, if the gate layer is made of polysilicon, it can also be n or p type. So this metal layer is also called the gate layer. And this is the substrate. Now some important things that we need to understand about this structure is that generally the gate is of a different material than the substrate. Even when the gate is made of polysilicon, doping in the gate is different from the doping in the substrate. Therefore there is what is called a contact potential between the metal and the substrate. In the case of the gate being a metal, the contact potential between the metal and the substrate is also represented using the work function difference, okay, and denoted normally as phi ms. That is work function difference between metal and semiconductor. So M stands for metal and S stands for semiconductor. So as we said earlier, the symbol M will be used in general whether it is a metal or whether it is a heavily doped polysilicon. So in general, there is a contact potential between the gate and the substrate, okay. This is one point that we must note. Second point to note is regarding the interface between silicon dioxide and silicon. This interface, that is this region, this region is of great complexity, okay. So there are different types of charges at this interface. These are called interface charges. Now in a simple analysis, what we do is that we neglect the effects of various charges at the interface. We also neglect the contact potential difference between the gate and the substrate. Now such a structure which does not have any contact potential difference between the gate and the substrate and which does not have any interface charges or even charges in the oxide layer. See, for example, this oxide layer may contain what are called mobile charges, okay. Although we don't want, during the fabrication somehow these charges may get into the oxide. So a device without any interface charges or mobile charges in the oxide and without any contact potential difference between the gate and the substrate is called an ideal capacitor. So ideal MOS junction or capacitor implies phi ms is equal to 0 and the interface or oxide charges, that is Q IT, that is interface trapped charge, Q OT, that is oxide trapped charge, QF, that is the fixed charge at the interface, and QM, that is the mobile charge in the oxide layer, all these are 0. So suffix T stands for trap charge, suffix I stands for interface and O stands for oxide. So QF is also an interface charge, suffix F stands for fixed. QM is a mobile charge, M stands for mobile, and this is in the oxide. So let us write this interface trap charge, this is oxide trap charge, this is fixed charge at the interface. And this is mobile charge in the oxide. So we will begin our analysis considering an ideal MOS junction or the capacitor. in terms of the terminal characteristics or the link between the charge conditions in the device and the external applied voltage, an ideal MOS capacitor means that when you apply 0 voltage between the metal and the semiconductor, there is no charge in the semiconductor. So let us consider the charge conditions in the device. So this is V, this is your oxide, and this is p-type silicon. When V is equal to 0, there is no charge in the device, either in the semiconductor or in the metal. So ideal MOS capacitor means no charge in the device for V equal to 0. Now we will start with the condition when the voltage applied is negative. What happens when the voltage is negative? We will start with this condition, then we will go to positive voltages. So when voltage is negative, basically the power supply is like this. So V less than 0. Let us try to sketch the electron and hole conditions in the device. So this is the oxide layer, and this is the hole concentration. Because it is a p-type semiconductor, the hole concentration is more than the electron concentration, and this is the electron concentration. So this is for V equal to 0. Now as compared to this, when you apply V less than 0, what will happen? There is going to be a negative charge on the gate, and correspondingly there is going to be a positive charge here. That is, you are going to have an electric field directed like this. Now how do you create a positive charge here? This is created by raising the hole concentration near the interface. Now when you apply a voltage, even then there is no current in the device, therefore the semiconductor is always in equilibrium. This is a very important situation associated with MOS capacitor that distinguishes the MOS capacitor from the PN junction. So this distinguishes the MOS junction from the PN junction, that even under applied DC bias the semiconductor is in equilibrium because there is no current flow. Therefore P into N should be constant and electron concentration will all dip down, so that this P into this N is equal to Ni square. Now we are plotting the concentrations on a log scale. Because otherwise we would not be able to show both holes and electrons. Now this is 1 and this is 2. Where 2 corresponds to V less than 0 and 1 corresponds to V equal to 0. So these are the conditions for holes and electrons in the device. Let us understand the shape of the hole concentration and electron concentration in little bit detail. Now what does this kind of shape mean? It means that there is a tendency for the holes to move from left to right because of diffusion current, because concentration is more on the left than on the right. Now this tendency for diffusion rightward is balanced by a drift tendency which is there because of the electric field created by the negative applied voltage. So electric field in this direction tries to oppose this motion because of diffusion. So this is drift and this is diffusion. So they are exactly in balance, okay? So that under steady state conditions you have a shape like this. At each point the drift and diffusion would be in balance. As you move away from the interface, the effect of the field will not be felt, and therefore you have a flat concentration. You can similarly argue for the electrons. I leave it to you as an exercise. Why is it that the electron concentration is falling down as you come to the interface? So one explanation we already given, that P into N should be equal to Ni square because the semiconductor is under equilibrium. Another explanation can also be given in terms of the balance between drift and diffusion. That I leave it to you to work out. Now what we need to do is, we need to see how these variations in hole and electron concentrations translate to a charge distribution. So we will sketch the charge distribution below, that is a space charge. Now to get the space charge, you recognize the fact that what is shown on the log scale, if you draw on the linear scale, this is what we had done in the case of PN junction. You will have a situation like this. So this is P, this is linear scale. The whole concentration for voltage less than 0. So for condition 2. Now we cannot show electron concentration here really on the linear scale. So this shaded area close to the interface indicates a pileup of positive charge. Okay. Now this charge is almost like a sheet charge. A sheet charge is a charge that is very close to the interface and it is almost like a sheet, and thickness of this charge is very, very small. Okay. Generally such sheet charges are because of mobile carriers, because mobile carriers can all remain attracted to the surface. They can move to the interface and then they can be held there by the electric field. Now notice also the fact that although on a log scale the variation does not appear to be that much, on the linear scale the variation is rather rapid and restricted very close to the interface. This is understandable because on a log scale this shows several orders of variation. Okay. On the linear scale a variation by a factor of 10 appears here, and the variation that occurs thereafter really cannot be shown. This point was discussed even in the case of PN junction. The difference between the appearance of a logarithmic plot or a plot on a log scale and the same function plotted on a linear scale. Now when you translate this information to a space charge picture, it would look like this. So you have a positive charge and an equal negative charge on the gate. On the gate it is again a sheet charge and occurs because of accumulation of electrons here, and this is the direction of the electric field. So if you sketch the electric field, that would look something like this. So this is space charge versus distance. This is the x direction. if you sketch the electric field will be shown on the negative side because it is directed from right to left, and it would be constant in the oxide layer because there is no space charge, and in the semiconductor it will fall rapidly. So it is restricted almost to the interface, and similarly in the metal also it falls rapidly. So this is the electric field in the semiconductor. Now this condition of piling up of holes in the p-type semiconductor at the interface when you apply a negative voltage to the gate is termed as accumulation. So the capacitor is said to be accumulated, that is pile up of the majority carriers at the interface, that is what is meant by accumulation. So this condition is referred to as accumulation condition. Now accumulation means pile up of majority carriers at the interface. Now we can easily relate the applied voltage to the amount of charge here, because our interest is in relating the charge in the capacitor to the DC voltage applied, right? That is the first step that we are doing in our analysis. So if this is the charge, this area under the curve is the charge. So this charge is Q. The voltage is given by the area under the electric field distribution. So this is V. We can therefore relate the charge to V, because by Gauss's law the electric field or this value can be related to the charge as minus Q by epsilon ox, that is the permittivity of the oxide. This permittivity epsilon ox is nothing but epsilon naught into epsilon r of the oxide, silicon dioxide. Generally the value of this is about 4 if the oxide quality is good. We can now relate the applied voltage to the charge in the semiconductor using this diagram. Since the area is V, clearly V is equal to this minus Q by epsilon ox multiplied by this distance, that is the oxide thickness. So this is nothing but T naught. So we write V is equal to T naught into Q by epsilon ox with a negative sign, which you can translate to Q is equal to V into epsilon ox by T naught. Now this quantity epsilon ox by T naught has dimensions of capacitance. In fact, it is strictly speaking dimensions of capacitance per unit area. You can see this as follows. The unit of epsilon ox is farad per centimeter, and the unit of T naught is centimeter. So this is farad per centimeter square. In other words, this capacitance per unit area. So normally this term is given the symbol C naught, because this represents the capacitance of a parallel plate capacitor in which there are two metal plates separated by the oxide layer of thickness T0. So we can therefore write the equation for accumulation as the charge per unit area in the capacitor is Q is equal to minus V into Cox. Please note that the voltage itself is negative for accumulation. Okay. So the charge in the semiconductor is positive. Always we are writing an equation for the charge in the semiconductor. What we can do is we can put a suffix s to indicate that we are referring to charge in the semiconductor. So accordingly we will modify our diagram here. We will put a suffix s here and a suffix s here. Similarly, we put suffixes s in these equations. Now we must clarify what is meant by the unit area. Students often have this difficulty. When you look at this capacitor, what is the unit area that we are talking about? Please note that the area that we are talking about is, if you take the 3D picture, this is how it will look. Now this is the area that we are talking about. Okay. So per unit area means this particular area which is perpendicular to the board is of unit dimension. So maybe 1 centimeter square or maybe some other unit. Okay. But that is the area. So when you talk of capacitance or charge by unit area, we are talking of, if you take a unit area of this, then how much is the charge. So that completes our discussion on the accumulation region of the MOS junction or capacitor, which occurs for gate voltage less than 0. Now let us move to gate voltage greater than 0 and see what are the conditions there. So now we are discussing V greater than 0. This means that here the power supply has this polarity. Now let us draw the distribution of holes and electrons for this condition as we had done earlier. So this is the oxide layer, and now for V equal to 0, we know this is our condition, holes and let us say these are the electrons on the log scale. So always condition number 1 is V equal to 0. Now starting with this, when you apply a voltage to the gate more than 0, you are going to create an electric field in this direction. Now this electric field obviously needs a negative charge here and a positive charge here. Positive charge in the metal is created by removing of electrons. Now how do you create the negative charge in the semiconductor? Clearly negative charge in the semiconductor will be created by attracting electrons or repelling the holes. This electric field will tend to repel the holes and attract the electrons. So therefore what happens is the hole distribution dips down while the electron distribution goes up. When you apply voltage greater than 0. as we have discussed earlier, even under applied bias the semiconductor is under equilibrium, therefore the P into N is always equal to Ni square. So this is concentration on a log scale. Now again, arguing as we had done for accumulation case, this electric field, what it does is it drives the holes away. So this is the drift current in this direction, and this drift current is balanced by a diffusion tendency in this direction, because holes are more on this side than on the left, so they tend to diffuse. So there is a diffusion tendency here. We will just make this diagram a little bit neater. So this is drift and this is diffusion. Now we can translate this information onto a linear scale. So first let us write here 2 means V greater than 0. So when you translate this information to a linear scale, it will look like this. The whole concentration, it falls rapidly. So by the time you reach this point, it has already fallen by a factor of 10. This is a log scale, just like what we did in a p-n junction. So here you have a depletion of holes. So in the depletion region, if you recall, the majority carrier concentration falls like this. So this is a fall by factor of 10 over a small region of width this much. So that is what is shown here, and then beyond that the concentration is really very small fraction of this concentration. Again, we are not able to show the electron concentration on the linear scale. Because even though the electron concentration is raised, still this maximum electron concentration is orders of magnitude lower than this whole concentration. So as a result, what you find is the charge that is required, the negative charge that is required, is created in the semiconductor by a depletion layer. So how does depletion of holes create negative charge? You know that in a p-type semiconductor in which there is no charge, the charge balance equation is given by P plus whole concentration, that is positive charge, is equal to the negative charge, that is N plus Na minus, where Na minus represents ionized impurity concentration. Okay. Now this ionized impurity concentration is responsible for negative charges in an acceptor type semiconductor or acceptor type doping. So that is what is happening here. When the holes are removed, the ionized acceptors are exposed and they contribute to the negative charge. Now that is why when voltage is greater than 0 and it is not very large, the condition in the capacitor is referred to as depletion. So depletion means removal of majority carriers. So in accumulation involved pile up of majority carriers, here removal of majority carriers. Okay. Now as you go on increasing the voltage further, what is going to happen? So if you increase the voltage further, obviously more of holes are going to be depleted and electrons are going to pile up. Now the voltage may be sufficiently large so that the hole and electron concentrations at the interface become equal. So it can be something like this. So this is condition 3. So let us remove these arrows so that it looks simple. So 3, condition 3. Now condition 3 corresponds to voltage when the surface concentration of holes and electrons are same. So let us write this here, 1, 2 and 3, all conditions we will list on the left hand side. So 1 is voltage equal to 0, 2 is voltage greater than 0, and 3 is a higher voltage, so V3 greater than V2. The voltage is such that Ns is equal to Ps, that is the surface concentration of electrons is equal to the surface concentration of holes. So surface concentration is the concentration at the interface. The terms interface and surface are used interchangeably in the semiconductor literature. So obviously when Ns is equal to Ps, since there is equilibrium condition in the semiconductor, both will be equal to Ni. So this is the condition. Now for this condition, if we want to draw the concentrations on the linear scale, how will it look? So you will have the whole concentration coming down much earlier. So this is 2 and this is 3. So the whole concentration starts here and then it falls, okay, on the linear scale. Again for condition 3 we are not able to show the electron concentration because you know Ni in silicon is of the order of 10 power 10, whereas this doping would be more than 10 power 14. So there are 4 orders of magnitude difference from here to here. So we really cannot show the electron concentration still, though it is piling up. Now you can go to even higher voltage, and at some voltage what will happen is this electron concentration will become equal to the whole concentration in the bulk. So let us draw that condition. So this is 4, and corresponding to this 4 electron concentration, the whole concentration would be something like this. So this is 4. Now this means that Ns is equal to P in the bulk, okay. So we will write it here as follows. Condition 4 is the voltage for this condition is more than the voltage for condition 3, and the condition on concentrations inside is that Ns is equal to P naught, where P naught refers to the whole concentration in the bulk, okay. Bulk means this region inside here away from the interface where the concentration is decided solely by doping and there is no electric field. So this P naught is the bulk concentration. Now, how do we draw the hole and electron concentrations on a linear scale for this case? So, moving this point away, hole concentration now will fall much earlier than this here. So, this is your hole concentration. But now, since this electron concentration here is equal to the hole concentration inside, you can show the electron concentration also. When you plot the electron concentration on a linear scale, you know, in a small region it would have fallen by a factor of 10. So here this electron concentration will look like this. For condition 4. So the hole concentration is like this, showing depletion of holes, and there is also an electron pile up here, which is now becoming noticeable for condition 4. Therefore, beyond this particular voltage, when the electron concentration at the surface becomes equal to hole concentration in the bulk, the surface is said to have got inverted. Okay, this is called inversion region. That is, in a p-type semiconductor, you are able to see at the interface a distinctly n-type behavior, because here near the interface you can see electrons are more than holes. Now, strictly speaking, inversion starts occurring beyond this condition, that is V3. Okay, because beyond this condition your surface concentration of electrons will be more than the surface concentration of holes. However, since you are not able to see much of an electron charge at the interface, normally one talks about inversion occurring only beyond a voltage 4. So another nomenclature for the inversion region is that for voltage greater than V3 but less than V4, when the electron concentration at the surface is more than Ni or less than P naught. This region is referred to as weak inversion. And the voltage beyond V4, when Ns exceeds P naught, is referred to as strong inversion. And the condition V less than V4, you also have depletion. So V greater than 0 or less than V4, you also have depletion of holes. So in this case, your P is less than yes, P is less than P naught. So now we need to separate the region V greater than 0 into depletion and inversion. So for small values of positive voltage when there is not much of electron accumulation at the interface. It is purely a depletion region. Beyond a voltage V3, when electron concentration at the surface becomes more than the hole concentration, it is inversion, but it is weak inversion because on a linear scale it is still not appearing, which means the amount of charge because of electrons is still small. Beyond V4, that is a condition when the electron concentration starts exceeding the hole concentration in the bulk, and then on a linear scale it starts appearing near the interface. A significant amount of electron charge starts appearing, and therefore we talk about it as strong inversion. So in a first course on devices, we normally do not treat the weak inversion conditions in detail. So therefore we separate the MOS capacitor regions of operation into accumulation, depletion and inversion. So this weak inversion region will be assumed to be part of the depletion region. Okay, so you have V greater than 0, depletion and inversion. So the depletion is for and inversion is for V greater than V4. Now, does this mean that there is no depletion beyond V greater than V4? No, the depletion region continues to exist, but what has happened is the inversion layer has started appearing. Okay, that is the meaning. Now again I want to emphasize, why is it called inversion? Because the electrons are becoming majority carriers near the surface, okay, in a p-type semiconductor. So it is almost like saying the nature of the p-type semiconductor at the interface has got reversed. Now more about this inversion region and the charge conditions in this region we will see in the next class. So in this class what we have done is that we have considered the MOS capacitor structure, and we have set our goal as explanation of the capacitance voltage characteristics of this structure for different frequencies, and then we started with an ideal MOS capacitor, and for which we have explained the accumulation, depletion and inversion regions of operation when you apply a DC voltage.